the CEO and co-founder of FuelTrust, which is a green tech SaaS startup that is presently solving the most impactful challenges to the maritime fuel industry. Jonathan is an engineer, an executive, and an entrepreneur who has led teams that were focused on product development, engineering, marketing, biz dev, support, sales, and M&A. His adventuresome career includes senior positions at Netscape, AOL, iNet Solutions, Mercator, Essential Software, and most recently, IBM. In addition to that, he has served on boards at universities, government programs, nonprofits, as well as being an advisor to several venture capital firms and tech startups. Ladies and gentlemen, help me welcome my friend, Mr. Jonathan Arneault.
It's my distinct purpose to not bore you. Since I'm between you and lunch, do so very quickly. So if we can. So what FuelTrust is, our first market is in the maritime fuel space. What you're seeing on the screen is a typical engine that goes into one of the ships. This is actually 1/3 of the engines. This happens to be a Wärtsilä slow speed diesel. The maritime fuels are let's just be plain about it, the dirtiest fuels on the planet. They are the last thing that you can possibly get out of a refinery. However, that being said, they have incredible energy potential. They are incredibly dense with carbon, and carbon is energy. And there are other chemicals within it. And so as a result of that, because they are the last bits that you get out of a refinery, they're the least costly fuels, which is necessary because the average large carrier gets somewhere between 8 gallons per mile and 21 gallons per mile, not miles per gallon, gallons per mile, right? So they require a tremendous amount of fuel to move literally tens and tens and tens of thousands of tons of materials in the most cost-effective means possible. Now, lately, maritime fuels, I'll go back one slide. Maritime industry is kind of getting dinged because they burn dirty fuels. That being said, they are, for tonnage carried by distance, one of the most efficient industries in the world. That being said, we are in a massive track to decarbonization in every industry. And the approach here is whatever we can do, however we can do it, as we're doing this with assets that have a lifespan of 30 to 50 years. These are incredibly expensive assets moving over the water, $100 million, $500 million and beyond for each one of them. So how do we solve this? Well, let me tell you, we built a platform, and I'm not trying to sell you this. I just want to kind of give you our approach. We designed a platform with the idea of, if I'm going to solve the decarbonization problem, I need to actually take it from its core. And that core is the fuels, how the fuels are burned, where the fuels are burned, and how are they then emitted after the fact. If I have energy, how do I make that energy the most optimal way in which I can consume the energy and emit the least amount possible? And so we took an approach to digital twinning on top of a platform that says, I'm going to use AI to actually understand things that today are nominally understood. We understand the chemistry from a chemistry approach. We understand the engine mechanics from a mechanical or from a physics approach. And the interaction between those is yeah, we think this is how it works, right? We look at what's the spray in a combustion chamber, what's the thermal units that come out of it. And we look at that from a physical aspect. And from the fuel standpoint, will this fuel burn and at what temperature? And then onward it goes. And yeah, it might emit some things, but that's those physics guys that need to look. And so how do we approach that? We put sensors everywhere. It's all lagging indicators. And yet what that does is, it's kind of like the stock market. It says, well, because we did this in the past, therefore this is what we should anticipate in the future, but past performance are not indicative of future results. And so our approach was, let's take this from a leading indicator standpoint. If I know the potentials within a fuel, and I know how that fuel will be used in the physical space, if I can take 2 digital twins and make them work together in a way that mirrors the real world, and that is the systems of systems approach. Ours is a bit strange in that what we're trying to mirror is fungible. Fuels change. Fuels are difficult. Every batch of bunker fuel is different from the batch that came right before it in the stream. And so we take this engine that we built. We have a patented AI digital chemist that actually looks at the molecules of each batch of fuel in every custodial handoff, and then even when it goes into the ship bunker tank. And then we take that digital twin, the AI digital chemist constructs a DNA fingerprint of that fuel at its chemical level. And then it takes the digital twin of the combustion chamber of that ship and predicts, if you buy this fuel and if you store it in your ship for X amount of time, this is what the output will be. And not just at a generic level, but a to the gram level, right? So how does that work? Well, first, you need to look at, in this case, maritime fuels. We can do this for any chemical, but maritime fuels have an incredibly dense array of mixtures of chemical components within it. It's gumbo, right? Gumbo is a single thing, but it's really not. That's what maritime fuels look like. By the way, that's what the gas in your engine looks like in your car. You just never see it, never think about it. And so, I can look at carbonium aluminum silicate. I have got calcium silicate there. I've got some hydrogen peroxide. I've got some NHO4, that's ammonia, right? I've got a whole bunch of stuff in there, except that's not just what it is. It's, a whole lot more, right? I've got a dense hydrocarbon. I've got potassium hydrate. I've got, let's see, what else? Potassium oxate, aluminum oxate, water, calcium not hydrate, hydrogen, hydrogen silicate, aluminum silicate. And then I go more and I've got more hydrocarbons of different scents. I've got more ammonia. I've got carbonium. I've got, let's see, that's calcium oxate, silicone hydroxide. I've got all sorts of chemicals. Oh, and it keeps going. These fuels have a tremendous amount of chemical properties that when you try to mirror them in a chemical structure, you pay a PhD a lot of money to go figure out what to do on this batch of fuel and what happens. So most people just don't. They say it's going to burn, and let's see what happens. It's in a class. It's going to be within a 4% range, one way or the other. Do I need to really worry about that? And by the way, there's about 750 additional compounds in the average bunker fuel, right? So incredibly dense. And so what we do is we take all that. We look at, in this case here, you're seeing a GCMS or a lab analysis of the fuel. And then we do some really interesting things. I don't want to give away our trade secrets, but we're able to take the trade documents as it flows through the life cycle of fuels, the things that everybody in the industry is already doing. And we capture those and we use AI to form a digital fingerprint of that fuel wherever it is. And we do some predictions with this twin. We say, if it sits under X amount of pressure and X amount of temperature, in a tank for a certain amount of time, it will degrade, it will sediment, it will, off gas. This is what it will look like because it sat in that tank for a certain amount of time. If I take two fuels and put them together, I still know what that fuel is coming out of it, but I'm going to tell you what will be the result. And when I find that fuel, now that blended or mixed fuel later on the supply chain, I know where it came from. I know what its properties are. I can predict any risks or failures or problems with it along its chain. So this is a digital twin of chemicals. And chemicals change, and so can the digital twin. And that's important for us to understand. Nextly, I've got to go look at my big monster engines. So I was speaking yesterday with Shannon at the dinner afterward, about a little bit of R&D here. One thing I need to note to you, we don't visualize our digital twin. Do you care to go see 842 different chemical compounds in a fuel? Nope, neither do I, right? Likewise, we don't need to create a visualized layer of these engines. Wärtsilä, MAN, Hyundai Heavy Industries, they're already doing those physical models. And even if they never did, it doesn't affect me. I care about the combustion chamber. I care about how it operates in the combustion chamber. What will happen to these chemicals under the chemical process of combustion? You got to think about it that way. Combustion is a chemical process. And so we approach this from the physical world as a chemical digital twin going into a physical digital twin or a physics digital twin. And so I model mathematically the combustion chamber for these engines. And each engine, by the way, not just, well, I start with an engine class. Let's say I'm going with a Wärtsilä 280 RPM heavy diesel motor. I look at that class of engine and its cylinder, which is probably about the size of that table right there, the cylinder head. And then when I classify that, what's its spray array, what's its combustion pattern, how is it going to operate? And I turn that into an algorithm. It's an algorithm. And then I load that in my AI for that engine. And then I watch the feedback of the physical sensors on that machine and or the engineering logs, because sometimes I don't have sensors. I've just got human beings who are actually reporting to me, this is what the fuel that flowed on mass flow meter, this is what the RPMs were, this is the temperature, this is the pressure. I'm collecting data however I can get it off of that vessel. My AI engine watches that and turns what is raw data into an operational digital twin. This is how this engine operates. This is what it behaves like. This is its changes over time at a certain RPM or speed or pressure or the combination of those. This becomes my algorithmic digital twin. Why is this important? Because you spend a gob of time trying to create graphical models and call that a digital twin. And what you really care about is how are things actually operating. The graphical model only helps humans. It helps us think about it as its meat space. But if I really consider, as if we did for power plants, I had a picture of the power plant, and I had little tiny, component knockouts that told me pressure and a number, right? Nothing changed in the graphics except the pressure array little indicator that came up to it. Why don't I do that when I'm creating my digital twins? And when and if I need graphical models, instead of spending 80% of my time trying to map out graphical models for things that don't have human interaction, I can save huge amounts of time, huge amounts of costs, and I can focus on how is it actually operating. And then if I do need to have a graphical representation, does it need to be real time? Does it need to be 3D spatial? It is if I'm doing mechanical maintenance on the engine. But if I'm looking at how do I optimize the engine, what's its inputs and outputs, I do want to have it as algorithmically done as possible. And if you want to have a scope of size of that, what those two guys sitting there are standing over, that's the turbocharger on one of these engines. That's just the turbocharger. You know, in my diesel engine, my turbocharger is this big. That's one of 4 turbochargers on this engine, right? So when we're talking about scale and impact of making conjoined digital twins functional, the scale in which we in this industry operate is massive. We can do this for arrays. We can do this for drill sensors. We can do this for fuels as they go through a refinery, because the percentage changes, the small changes we make through the whole life cycle of making these digital twins, this operated and this operated, the systems of systems, is not simply recording or reporting. It's now beginning, as our prior speaker said, it's about actually physically operating, automating the operation of our infrastructure, not to take people out of the loop, but to make things happen faster and augment the human in the loop in order to make better changes and better understanding and enhancements. So what we do here is we look at each engine type, we learn each engine's profile, and then in the actual vessel or system we're doing this for, then that digital twin self-learns, self-enables, self-enhances over time. And then what happens if I change the piston rings? Guess what? My AI engine says something changed. Go reset your learning with back propagation of information that's coming out of that engine and update your engine's profile, your efficiency index, your carbon intensity index, et cetera. So what we do, we take the combustion digital twin with the chemical digital twin, and then we actually put the runtime parameters through it. And so I can tell you, when you burn this fuel, this particular batch of fuel that happened to have a significant amount of aluminum in it, because that's the way it came through the refinery, that this will be the sediment particulates of aluminums that will sit in the bottom of your chamber. This particular fuel, because it has a high amount of calcium in it, is actually going to put out much more black carbon as the carbon and the calcium combine together, and then off gas because it's a microparticulate. I'll be able to tell you that. And I will actually be able to tell you to the gram, we won't say that today, to the kilogram, but if we can to the gram, tell the amount of CO2 you produced. What's the amount of carbon monoxide versus carbon dioxide? What amount of water vapor did you produce? What amount of SOx did you produce? How much NOx did you produce? How much other particulate matters? We actually produced today a report of about 28 different emission classes that can come from the fuel as it goes through the engine. And I go one better, because I now have created a digital twin of the chemistry of the fuel. I'm decommoditizing fuels so that when I am making a purchase in this case for bunker fuels, where I'm buying anywhere from 1,000 to 10,000 metric tons or 8,000 barrels at a time, I'm able to say, you know what? The fuels that are in tank 27 of the same provider versus the fuels that are in tank 42, not only are they better for my engine, that fuel will lower my carbon tax because its model of working through my engine is better than tank 40. There's nothing wrong with tank 42. But because tank 26, its carbon potential in the way it operates in my engine will have a better outcome, even if I'm paying a little bit more on a price per barrel or price per metric ton, I'm going to save that money on the backside of emissions when I have to pay my carbon tax if I'm in Vancouver or in the EU or I'm in Singapore or California. Now I'm differentiating a commodity based on its outcomes before I even bought it. And so we're able to get ahead of the curve. Ship companies, in this case, and in the near future, and industrial fuels as well, will be able to differentiate the fuels they buy, not just on price or class, but on the actual potentials, using the digital twin of the fuel, its potentials, and the devices, the machinery that consume that. Not just a super system like an oil rig, right, with 20 million moving parts to it, but here, disconnected digital twins, a digital twin of the consumable and a digital twin of the thing that is consuming, working in a super cycle. All right. And you can't do that if it's simply a physical model of a physical world. Here, we've taken the algorithms or the data sets, turning them into algorithms, such that now I can ingest and output information that's meaningful and actionable, both ahead of time and post-consumption or post-usage. All right. Now, how does that go beyond fuels? Well, I will tell you, there are some economic outputs that happen to that, but I can do the same thing when I'm buying physical equipment. Same thing we've kind of done for 20 years with AutoCAD or MATLAB and other physical simulations or design systems. But what if instead of just handing somebody my CAD file, my .cad or MATLAB.mat file, I actually am looking about, I need the physical parameters to do X, Y, Z. You design to give me the inputs. And then I will model around that from a physical interface and or an operational interface. The methane production or the methane off-gassing that we saw earlier, what if I want to model, as we're seeing in places like Wyoming and here in Texas, people actually want to take that gas and they want to go mine cryptocurrency and other things. And so instead of just, literally just, small leakages amount that are, being combined together, how do I now commoditize that in such a way where I'm giving that information in a digital twin approach or an algorithmic approach so that others can now, they can design the solution to my problem because it creates opportunity for them as well, right? I want to capture some of that methane or natural gas that is naturally, off-gassing in the world. I want to capture that and now turn that into energy. And so again, some of the things you can do when you plan for that. In my solution, and I can't solve everything in the world for you, but with our solution, by taking this differing approach to digital twins, loosely connected digital twins, and how do they interact in the real world space? Firstly, I can get insights into my emissions before I ever bought something, not just a spreadsheet number, but a real world number about the exact fuel that I'm looking about buying. Nextly, I get visibility into the fuel's performance and risks. Well, this fuel's got way too much of a paraffin instead of a aromaticity count, and that's going to cause problem with the remaining fuel on board in the vessel that I have. I can have an exacting analysis of what my emissions will be pre and post use. And then more importantly, for energy producers, my potential customers differentiate me on what I'm producing. And therefore, I produce something differently because I get insights into what was the outcome of my fuels. I can actually now know what happened when my customer bought my fuels and used it in their equipment. And then I also can then optimize the fuels that I blend or I manufacture for the real world use cases, and kind of just, instead of just kind of large scale guessing or grouping that together. And then lastly, the costs of transitional fuels. If I can produce methanol, if I can produce ammonia, if I can produce hydrogen, well, I've got a whole set of industry of real world physical space out there that I've got to accommodate for. What if I can partner with my customers around this idea of digital twins, instead of just sending it back to the manufacturer? I've got a fuel. How can I test that out in the real world? Digital twins not just allow me to test it, they allow me to test against real world machines in an algorithmic way that allow me to reduce the risk dramatically instead of, okay, let's just go take LNG and a whole lot of lubricant and then run it through that other engine and see what happens. Now I can get insight ahead of time and tell not just, all right, it runs, but what will be the emissions output overall, not just did I get rid of carbon or did I get rid of sulfur, et cetera. All right. And so we are seeing, because of this, a significant amount of CO2 savings on existing fuels by giving them real world reports. By looking at a bunker fuel, not just saying, yep, this one was better than that, but I'm looking at the actual oxygen that's already in the fuel, and I'm looking at the hydrogen that's in the fuel, I'm looking at the ammonium in the fuel, and how do they combine chemically, instead of just saying for every atomic element of carbon I've got, add 2 for oxygen, and then I do my number. Now I can actually say, no. You actually, when you ran that fuel, produced not 82% CO2, but you actually produced 72% CO2 because of the makeup of the chemicals within it. I'm giving exacting information that allows me now as a company to tell real truth about what I did, and therefore that benefits my entire downstream life cycle. So with that, I am at end. How'd I do? All right, and Mr. Shelton. Oops, I've got one question. How do I get there? Oh, and if you want my contact, that's why. I don't see the question. Right behind me. Oh, here we go. Could you comment on the digital twin of particulate filters that are reduced to do small scale particulates or SID emissions? Yeah, so the particulate filters are like the engine. We will take that and look at their operational parameters. And this it's not really a scrubber, but it kind of works that way. And by the way, we model for scrubbers as well for CO2 and most importantly for sulfur. Those particulate filters have an operational parameter and they clog over time, right? They fill up and you got to clean them. And so just as we do with the engine physical parameters, we would look at those filters that are coming through an array. It's kind of like a centrifuge. And what is their operational parameters and what was their load, right? How much particulate was sitting in the ashtray? How much are they operating at efficiency? What was the temperature and pressure? All of those are actually physical, real world, plus the emitted exhaust at temperature and what were the particulates that came out of that combustion process. So very much as the input in the combustion, as it goes through that stack, it's going to hit the particulate filter and then it's going to hit the scrubber if there is one. And so that becomes part of the physical world model or physical analysis that we put into an algorithm, right? And not just us. I mean, this is something that you would want to do when you design a ship, when you design a power plant, when you design a refinery. Not just give a raw number there, but how do I measure that and how is it operating in efficiency? Hopefully that answers the question. All right.
All right. If you've got more questions, I'm sure he has more answers, just like Radio Shack. Feel free to find him after. It's time for lunch. Encourage you to network a little bit. And we will meet back in here in about 50 minutes, 45 minutes, 1 o'clock. We'll be back. See you shortly.